Well, hello, folks. We'll go ahead and get started. Looking forward to sharing some more information with you. So let's open up in prayer, and I'll give you a rough sense of the material we'll focus on today. So, dear Heavenly Father, Lord, I pray that you would be working in the lives of each of the students in this course, Lord. I pray that the material will be clear. Pray that it will be interesting, Lord, and I pray that it will be helpful for them as they're seeking to secure the job of their choice in their future. Pray that you also help them in their character development, Lord, in their spiritual development, that all the times that they're spending studying scripture, that will be things that will be helpful for them. They can cherish that in their heart. And also I pray that you would help them with that as they're understanding the theological concepts that we want to be deriving from that and how to be guiding our lives. Give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, we're in an interesting place right now. And so we got about halfway through the chapter on searching. We briefly went over it and then showed one of the video notes that's associated with that. And so depending how the time goes, I'll go through that and then begin to introduce the whole idea of dictionaries. And one of the ways of doing that is we'll be adding another way of thinking about generics by adding not only just one generic, but two, because with a dictionary, you have a key and a value. And so we'll want to get a chance to be thinking about that. Well, let's think about what we have here in searching, because we've been thinking about sorting for a while now, several chapters. Now, this is the other thing that we need to do, the searching and sorting is with these more complex abstract data types that we're getting into, that's going to be important. So we have these four different possibilities. We can have an array that would be for two options, and then a chain or a linked chain for two things. And so we can either have an unsorted array, a sorted array, an unsorted chain, or an unsorted or sorted chain. So this gets into the implementation, but we're thinking in general about what is the significance of being sorted or sorted, unsorted or sorted. And it turns out for searching, if it's sorted, that's going to be helping out quite a lot. And with the binary search, that's the strategy. So binary is either one or the other. So we can divide it into half, and then we can divide it into a quarter and then eight. And so we can very easily narrow down to what the actual element is that we're searching for in that fashion. So we talked in general what it is like to be searching in everyday life, searching in a drawer, searching in our closets, or searching for a name, maybe trying to see what our grade is in a list that's posted outside an office. And so those are some things that are there. So we talked about things for an array, and so this is a little bit of a reminder. So this is using a loop to search for a specified entry value. And so while it isn't found and it's less than or equal to the length of the array, we cycle through and see if we can find it. And so this is a general way of how we could be doing this in an iterative fashion. So I think the video note did a better job than what's here in the lecture notes. So I'm not going to dwell on this, but this just gives you an idea of how to be sequentially looking for things and searching in an unsorted array. So we can also have a recursive approach. And so we got introduced to that also in the video note that we showed in our last time together. And so this is just a reminder of what that code is. You guys all have access to this code. And so there's a zip file that I've shared in Canvas if you wanted to get a heads up for each one of these elements. So as you know, with a recursive, we actually are calling the method or class within the class method. So here we have a method, and we have a case where we do it one less than what it was before, and so we gradually work our way down to getting the total array that we have searched. So this just gives a little bit of a sense of how we go doing it with a sequential search of an array. There's all kinds of things we can do. Maybe some of you like collecting coins. When I was growing up, that was something I thought was kind of fun. And so, but then when we have a sorted array, this is, God forbid we ever do this to one of our books, but this is in a sense is what we find. So it's either less than or greater, and we're looking for a certain thing. We can first half, we just get rid of half the book, and then the half of that, which would be down to a fourth, down to an eighth. And this is just a way of giving a sense what the whole searching methodology is for a binary search. So this is now just some more stuff that walks through the details of how a binary search works. And so this, for a sorted array, it's going to be a lot faster for it to converge to the right value. So here is the code. We got a chance to see this in the video note as well, but here's just another example of us getting a chance to be seeing it. We can see that some of these statements that we're starting to have are getting a little bit more complicated. And so we can just make sure that we're mindful of that. So we, like before, if we're going to compare and searching or sorting or things where we have to compare, we're going to have this comparable factor in it. And so that's something that hopefully by now is getting more and more familiar to you. There are various things that are built into Java. I would also just have you remember that we're doing two things. We're doing the backend programming. We're also doing the front-end application development. And so we're having two types of programming that we're getting exposed to from this. And so this gives us a little reminder of something that's within the Java language itself. So we'll have a summary chart at the end of this chapter, but here we see the how for a binary search of an array that is sorted, we can see that it definitely is going to help out. Instead of big O notation n, it's log n, and so that's an improvement. Well, then we get into having the chain implementation of this. And so this is just a rough idea of what it would look like, that chain. Each chain points to the next element. That's stuff that we've talked about it. So first of all, we have an iterative solution for contains. And so we're trying to see where it is. And so as long as we haven't found it yet and the current node is not null, which means that we're at the end of the chain, we're going to keep looking. And so that's the general scenario that we have here. And so and if we find out that we're not at the end of the chain, then we want to be doing this comparison. And so, and if not, then we're going to go to the next node and continue to do this. And so this is just an iterative way of walking through that. Here we have a sequential example of this. And so we have search, and then we have a scenario where within that we're going to call again recursively search. And so that's what we have for our private method search, but the one that's available to the user is contains. This is a public, and so it's either contains or doesn't contain it. So we're going to return that Boolean, and then it's going to call this private method here that shows you those details. Here is the implementation of an iterative search in contains. And so just using a while statement, we one at a time, we go circle through to see whether or not we found it. And so that's what we have. And now this is for a sorted chain rather than an unsorted scenario, which we just mentioned. And so this is just a general way of looking at it. Then the other thing is we wanted to be looking at a binary search of a sorted chain. So but first we want to find the middle of the chain. You can traverse the whole chain. then traverse one of the halves to find the middle of the half. And so in conclusion, it's hard to implement and less efficient than the sequential search. So maybe that's something that may not have been intuitively obvious to start out with, but these are some of the caveats we want to be thinking about. So here we see a couple different examples here. So we have here is the time efficiency of the searching expressions in Big O notation. And so for a sequential search for unsorted, the worst case scenario is Big O notation N. And so here we have the summation for things that are in the linked scenarios. We have the sequential search. And so that's what we have. And then the binary search, instead of Big O notation N, it's down to log N. So that's definitely going to be an improvement. So then we finish up with thinking about this searching by asking some of these things, and which is better, the iterative or the recursive search? And so the iterative search can save some time and space. We saw that was true for an array. Recursive search will not require much additional space for the recursive calls. Coding binary searching recursively is easier. And so those are some pros and cons that we can be thinking about as we're going through that. So I'll show the video note in a second, but I'm going to press forward a little bit more with some lecture material. So let me just see if you guys are tracking what we have there for what we're talking about with searches. Does that make sense? You can, okay, good. Okay, well, we'll continue on and we'll just do a little bit of an introduction. First, a little bit of a precursor for something that we're going to be leveraging for Java, and then we'll introduce some of the concepts that are there that are used for a dictionary. So this is just a short little few slides that's for this Java interlude. And so you can have more than one generic type. And so this was where we just had a single generic type T. So that's something that we've seen in the past, but it's possible to find more than one generic type. And so we're going to be starting to think about a value, a key and a value. And so we can be using K and V. And so we write identifiers separated by commas within angle brackets after the class's name. Each represents actual data type specified by the client when it instantiates the objects of the class. So like before, we could have a dictionary of phone numbers, we could have a dictionary of addresses, we could have a dictionary of word meaning. And so we can have that relationship, the key and the value could change based on some other things that we're doing. So this was what it would look like. So you can have a pair of say an S and a T. So we're having two fields that are being passed into this class. And so that just gives you an idea of what it would look like. And so we then, with that information in a constructor, we have the first item and the second item, we put them into local variables, and then we could do something. And so here we're doing something simple. We're just putting that into a string and returning that information now hosted as a string. So that just gives you an idea of what you can be doing with that. And so here we see some examples of the class pair. So we set up the name for Joe, and so Joe and his last name is Java. We also have his phone number here, and so we could actually create now with this latest class with the pair, we can put his name, his first and last name, associate, and as well as his phone number, and put that all into a complete entry, a dictionary entry for Joe. And so it has Joe and then has his phone number all like that, and we'll print it out, and it will be Joe Java and then his phone number. So that just gives us a rough sense of what that's all about. Well, then, as we get into dictionaries, and I'll just walk through this just to give you an idea of some of the things that you can be doing here. And after the break, we'll review some of this before we continue on and some of the additional details for dictionaries. So in this chapter, we talk about the specification for the ADT dictionary. What are the methods that we have to implement? Then we'll talk a little bit about the iterators, how we can have an iterator for the key, an iterator for the value, or have them both going on at the same time. And then we have like 3 different examples that are discussed: a telephone directory. So that gives you a name and that gives you a series of numbers. And so those would be the first one. You can have the frequency of words. And so you can be counting how often that word is in a sampling of text. That would be something that you could consider. And then you could have another example, a concordance of words. And so this word is like this. And so you can have that relationship that's shown. And then also talking a little bit more about what's built into Java, we have the interface map. And so we're calling it dictionary. There's other words that are used for a dictionary kind of capability, including the term map. Map is what is used in C++. So we use dictionary in a variety of different ways, looking up a meaning of a word. And so say like a Webster's dictionary, we can have an address book. We can have a phone number. So we look at a telephone directory. We can have a contact on our phone. All of these are using this data structure, this abstract data type dictionaries. And so these all can be implemented with an ADT dictionary. And so that's something that is useful for us to think about. So what are the specifications for a dictionary? Some of the names that you'll hear associated with this would be a map, a table, or an associative array. And an entry in the dictionary contains a keyword or a search key and a value. So a key and a value, key and a value. Hopefully you'll start to be picking that up and have a little bit better memory of those 2 key things. This is K and V. So K is a search key, V is a value corresponding to that. So for every search key, there's a corresponding value. There's at least 1, if not more, corresponding values. And in the next handful of chapters, we'll be getting into what that entails. Here are the different methods that we need to implement: add, remove, get value. Those are things that we're familiar with. Contains, that's also something. And we have these iterators. And so we will have some private classes for these iterators that we're going to be setting up. We'll have a couple other things as empty, get size, and clear. Those are some things that we have already seen in different types of ADTs. Well, this just walks through each one of those methods in more general, in more details, and gives the parameters and what's returned. So thus, if we were to have this associated with some of our extra things that we're making available to a customer, it would look just like it's just something that was built in Java in the language. So those are the different methods. And so thus, a key thing that's important for us to do in dictionaries is having these iterators. And so thus, searching is very important in dictionaries. And so the work that we did leading up to this concept is very, very much something that we want to make sure that we consider. So we can use each of these iterators either separately or together to traverse all search keys, all values without traversing the search keys, and all search keys and all values in parallel. And so thus we have these 3 options. We can search with the key. We have that. We can be searching with the value, or we can actually do both. And so we can have these things actually going on at the same time. And so those are some possible things that we can be thinking about as we're going through that. And so within a dictionary, we have this key and a value. And so thus we have these things that can be 2 different things that are associated, say. So here we're thinking for a telephone directory. So it's going to have a phone number and a name. And so we could be storing that phone number as a string, and then we have the name. And so those are the things that we're seeing in a dictionary. And so for this example, we're looking at it for a telephone directory. Does that make sense? Everybody following along what we're doing for this introduction on dictionaries? So, thumbs up if that's making sense for you. Okay. So then we get into these several examples here. And so we have a telephone directory. So first of all, we have a driver. The next chapter, we're going to get more into the implementation. So this is just trying to give us a higher level sense of what's going on with a dictionary. And so we have some things that would be kind of nice to have a few things, an input error and quit. These are some variables that we'll be utilizing in our implementation. We notice that they're final and static, so we can't change them. And then we have our main. And so here we're setting up a new directory of type telephone directory. And so we're going to be reading in a file from data.txt. And so that's what we have here in this situation. We've seen a lot of the sample drivers. We just manually have lines of code that puts things in. Another possibility, and for your data set, some of you may actually be using this approach where you're just loading in a text data file that has a proper delimiters, like a carriage return or something like that. So then we read in that data. So from that file name, and then our directory is going to have that data loaded into the directory. And we have a try catch block here. And so if that file is not found, which would be a good thing to find out at the beginning, rather than trying to guess where the error is, we have this. And so we can have a descriptive message that we can include as well. And so we got that, we got the file loaded. And so as long as we're not in this situation where there's no data, we're going to skip down here. And so once again, another check if the phone number is null. So first we check the name, then we check the phone number. If it passes that, then we print out that the phone number for a certain person is this phone number. And so that's how we can get a chance to see this. Finishing out there for the implementation for a driver for a telephone directory. A few more things here. So here we have the name. And so this is a private method that's called here. And so in some of the previous things that we've looked at, so this just spells out the how we return either the name from the user or these other error conditions. And so that's what we have there. And then just finishing up here, finishing up the lines of code in support of that information for the telephone directory. We have some sample output here. And so we can enter the name. And so then it gives us it tells us who Maria's phone number. Then we stick in Hunter. Well, that's not a full name, and so it gives us an error message, but it allows us to continue. So if we put Hunter Smith, and it says that that person is not in the directory, and finally we quit. And so this is one of the keywords that helps us to engage with that command line interface in a clear way of that. So we had the driver. Now we have a chance to be looking at the implementation of the telephone directory. And so this is going to be a sorted dictionary with distinct search keys. And so this is going to make it a lot easier to look up a number if it's sorted. And so it's alphabetical order. And so thus we have an example of what's being laid out in this situation. So we have this dictionary interface. It has a name and a string, and we saw that with a UML diagram a couple charts ago. And so, and then we're calling it phone book. So then we have the constructor. We're setting it up as a new sorted dictionary. And so thus we got that initialized. So it's going to consist of three things: a first name, a last name, and a phone number. And so we have all of that stuff here with some methods that are helping us to interrogate that data from the file that we've read in with our scanner. So so then we have a couple of setters and getters. So we have the get phone number with the name of a person, and then we have the get phone number. So we put the name in, it's going to return the phone number. And so those are the ways how we can implement that. Here we have another example of frequency of words. And so we use a scanner to read in our sample. And so then we're going to interrogate that. We load that into our dictionary. We have a try-catch block to find out that there is a file. And so sometimes it can be a little bit tricky. You want to make sure that you spell this name right, that it's in the directory that your program can access. And so this can actually be a useful thing to have in this case to make your troubleshooting a little bit easier. So this is the overall driver for that. Then we have the implementation of the frequency counter. So this is public, and so this is made available to the user. And so we're having setting up a dictionary, a word table. And so we have our constructor. We said a word table is equal to a new sorted dictionary, and it doesn't have anything when we start out with. So here we're setting up a delimiter. And so that's another nuance I'm not going to get into in too much detail right now. And so while there is some additional data, it's going to read all of those things. Next word. And we're going to be setting up frequency. And so those are things that we have here to help us getting going. So thus we have the read file of the frequency counter laid out here. And then just finishing up, we have another public method to display. And so this is where we get the key. So we're going to be using the key iterator and the value iterator. And as long as there's something next, it's going to one at a time print out what is the key and what is the value. And so this is a way of just listing out what is the frequency count for each of these values after we've done this first step of interrogating that data. Then we have a concordance of words. And so this concordance provides a location of a word. So it could be a page or a line number. That's how they're considering what this would be. And so we have our class concordance. And so we have using the dictionary interface and we're list with iterator interface where we're initializing the word table. And so that's concordance. We have this word table is a new sorted dictionary. And so we have this constructor for initializing our concordance. Then getting into some details here. Here we have the method read file. And so it reads a text file of words and creates a concordance. And so while there is another item, we use the scanner to process a line and load it in. And then we do the word count for each line as long as there's another line. And at the very end, we close the scanner to finish off that part of the code. This is for the read file. So then we have the display, and so we use the key iterator and the value iterator. And so one at a time, we just list the concordance of the words. and then we close things out. And so that's just a high-level introduction to that. And this is just the last chart I'll talk about for the lecture portion. These are some of the things that are out there that we can be leveraging. And so this is the Java class library, the interface map. I'm not going to really dwell on this. We're really trying to focus on our implementation as we do an introduction with ADTs. Any comments or questions on that? Okay, thumbs up if that's clear, at least for an introduction. Okay, we're going to be spending some more time on this. So I'm going to go ahead and do a few video notes. So we did the array searching. I'll do the linked list, and then we'll do a couple for the dictionary. And so, and then I'll pop over to Eclipse, and we'll look at some examples of the searching routines that we've been introduced to today. Okay.
Within a linked implementation of either the ADT list or the ADT sorted list, the method contains searches the chain of linked nodes for the target. As we'll see, a sequential search is really the only practical choice. Let's begin with a chain whose data is unsorted, as typically would be the case for the ADT list. Regardless of a list implementation, a sequential search of the list looks at consecutive entries in the list, beginning with the first.
So they did say that a sequential search of a linked data list is the best way to go. So we kind of mentioned that a little bit when I was going through the lecture notes, and we're getting a chance to have that reiterated to us here.
First one until either it finds the desired entry or it looks at all the entries without success. When the implementation is linked, however, moving from node to node is not as simple as moving from one array location to another. Despite this fact, you can implement a sequential search of a chain of linked nodes either iteratively or recursively, and with the same efficiency as that of a sequential search of an array. While it's clear that a method can access the first node in this chain by using the referenced head, how can it access subsequent nodes? Since head is a data field that always references the first node in the chain, we would not want our search or any other aspect of the list to alter the reference to head. Thus, an iterative method contains should use a local reference variable current node that initially contains the same reference as head. To make current node reference the next node, we would then execute the statement current node equals current node get next node. When done recursively, a sequential search looks at the first entry in the list, and if it's not the desired entry, searches the rest of the list. How would you implement the search of the rest of the list when the list entries are in a chain of linked nodes? The iterative method contains that you saw in the previous segment uses a local variable current node to move from node to node. A recursive method would not have current node as its local variable, since current node would get reset to an initial value at each recursive call. Instead, such a method needs current node as a formal parameter. But then we would have a method whose parameter depends on the list implementation, making it unsuitable as a public method. Just as we did in earlier lectures, we'll make this search method private and call it from the public method contains.
So as we saw previously, sometimes there's a way of fixing maybe a shortcoming. And so now this is what we're getting a chance to be seeing this for a linked implementation. We change this to private. And we're going to be passing this current node in that way.
The private recursive method examines the list entry in the node that its parameter current node references. If the entry is not the desired one, the method recursively calls itself with an argument that references the next node in the chain. Notice that the call to the method search initializes the parameter current node to head, much as an iterative method initializes its local variable current node to head. The efficiency of a sequential search of a chain is really the same as that of a sequential search of an array. In the best case, the desired item will be the first one in the chain. Thus, at best, the search will be order of at most one, since you will have made only one comparison. In the worst case, you'll search the entire chain, making n comparisons for a chain of n nodes. Therefore, the sequential search in the worst case is order of at most n. Typically, you'll look at about half the nodes in the chain, and thus the average case search is order of at most n over 2, which is just order of at most n. Now let's search a chain whose data is sorted. Such a chain would occur in a linked implementation of the ADT sorted list. Searching a chain of nodes whose data is sorted is similar to sequentially searching a sorted array, as presented in an earlier lecture. Here, we incorporate that logic into an implementation of the method contains. Notice that we iterate through the list until we reach the end of the list, or we find an entry whose value is greater than the target for which we're searching. Once the loop terminates, we need to test which of the two conditions failed. If we reach the end of the chain and did not find the target, this test returns false. If we stop because we reached an item that's not larger than the target, and the item is not the target, we failed to find the target. Otherwise, we terminated the loop before reaching the end, and the entry that was not larger than the target had a value equal to the target, so we succeeded in finding the target. A binary search of an array looks first at the element that is at or near the middle of the array. It's easy to determine the index of this middle element by computing last minus first divided by 2 plus first, where first and last are the indices of the first and last elements, respectively, in the array. Accessing this middle element is also easy. For an array A, it is simply A sub mid. Now consider searching a chain of linked nodes, such as the one here whose nodes are sorted. How would you access the entry in the middle node? Since this chain has only 3 nodes, you can get to the middle node quickly. But what if the chain contained 1,000 nodes? In general, you need to traverse the chain beginning at the first node until you reach the middle node. How will you know when you get there? If you know the length of the chain, you can divide the length in half and count nodes as you traverse. The details are not as important as the realization that it takes a bit of work to access the middle node. After looking at the entry in the middle node, you probably need to ignore half of the chain and search the other half. Don't change the chain when ignoring part of it. Remember that you want to search the chain, not destroy it. Once you know which half to search, you must find its middle node again by traversing the chain. It should be clear to you that a binary search of a linked chain of nodes would be challenging to implement and much less efficient.
So you can see here's an example with these 4 options that we had for searching, that this isn't really a good option. You get an n squared, big O notation n squared. That's just something you definitely don't want to do.
A sequential search.
So sometimes I use an analogy of like a handyman, and you have your various tools that you use. And so there's times when one tool is better than another. And so here we're getting some insight into how that is for this. Okay, so that's the other video note on searching. And now we'll get a chance to be thinking a little bit about a dictionary, how we were going to be apply searching and sorting. And so you would think that you add something to a dictionary, you would definitely want it to be put it into that sorted location. There's going to be a caveat. We're going to get into something called hashing, but I'm just going to start with that and say that's a truism, and we'll touch again on that in a little while. So let's do this first video note. This is the ADT dictionary, just a general overview of that.
This lecture introduces the concept of the ADT dictionary. If you need to check the meaning of a word, you look it up in a dictionary. If you need a friend's address, you consult your address book. If you need someone's telephone number, you check your list of contacts on your cell phone or use a phone telephone directory or search for it online. Each of these examples involves a kind of dictionary. This lecture describes and uses an abstract data type that generalizes our everyday notion of a dictionary. The previous examples, such as finding a word's definition, a friend's address, or someone's telephone number, are all examples of searching a dictionary.
So I'm hoping by now you're starting to get an idea of what an abstract data type is. We're giving several examples. We saw some nuances. We had list, and then we had sorted lists. We had queues, decks, and priority queues. And so there can be some things that are slight deviations, but you're going to see that there might be some special thing that you're trying to cover here. Now we have a dictionary where with the first time that we have this association, this collection of something that's related to another item. And so maybe you can think of, if some of you guys are into sports, and so you can think of the name of a player and his batting average, or the things that we've already talked about, like a phone book or something.
In a previous lecture, we examined how to search a list. We'll see that a dictionary provides a more powerful way to organize data that will be searched. The ADT dictionary, also called a map, table, or associative array, contains entries that each have two parts. A keyword, usually called a search key, such as an English word or a person's name. Some dictionaries have distinct search keys, but others allow two or more entries to have the same search key. For example, a dictionary of student records organized by student identification numbers has distinct search keys since those numbers are unique. On the other hand, an English language dictionary has duplicate search keys, since it often has several meanings for a word. For example, my dictionary has 3 entries for the word book. One's a noun, one's a verb, and another is an adjective.
So that's an area of complexity that we're going to be getting into in some follow-on chapters. But just I wanted to have you think about, just in general, having a key and a value relationship. And what if you have 2 people by name John Smith, for example, or they mention different meanings of a word? All of those are things that could come out.
A value, such as a definition, an address, or telephone number, is the other part of an entry in an ADT dictionary. It's associated with a particular key. The search key enables you to locate this desired entry. Here is an example of a glossary that could be from our textbook. Each entry has a word as the search key and the word's definition as the value associated with the key. In general, the search keys and values in an ADT dictionary are objects. Each search key is paired with a corresponding value. The ADT dictionary organizes and identifies its entries by their search keys rather than by another criterion such as position. Thus, you can retrieve or remove an entry from a dictionary given only the entry's search key. The fact that every entry in a dictionary has a search key distinguishes the dictionary from other ADTs such as the list. Although you certainly could put an entry that has a search key in a list data is organized by position, not by search key. Printed versions of the Natural Language Dictionary, a telephone directory, a library catalog, and a thesaurus all have entries sorted by search keys. These databases are dictionaries, but the ADT dictionary does not necessarily require that entries are sorted. Why do our examples of printed dictionaries sort their entries? This makes it easier for the reader to find a particular entry. In contrast, if you searched a computerized thesaurus for a word, you would not be aware of the order of its entries, nor would you care as long as you could retrieve a particular entry. Thus, whether a dictionary has sorted or unsorted search keys is more of an implementation detail than a necessary characteristic of the dictionary.
So that's another feature that we're going to get to right now, where things like hashing, which we'll talk about, sometimes in unsorted dictionaries, it can work just as well, but there's something else that you've done to make it so that's the case.
But remember that the details of any implementation affect the efficiencies of the ADT operations in various ways. The ADT dictionary has the same major operations, insert, delete, retrieve, search, and traverse, that are common to most databases, even if a particular implementation sorts its entries or allows duplicate search keys. Because we're finding items based on search keys, an important design decision we must make is whether or not to permit duplicate search keys in our dictionary. If we decide on distinct search keys, the method add can ensure that the search keys in a dictionary are distinct.
So here we have a scenario with there's distinct search keys. So if you're trying to add John Smith twice, the second time it should give an error message. And so that's going to be something that's going to be hard coded in your implementation. If you allow for multiple instances of John Smith or the same search key, then there's going to have to be some other criteria that you're going to have the distinct values that are going to show up. And so that's something else that you're going to have to explore.
If a key is already in the dictionary, the operation add a particular key value pair could either refuse to add another key value entry or change the existing value associated with the key to a new value. In this second case, the method will return the old replaced value instead of not having any output as indicated earlier. Regardless of how add guarantees distinct search keys, the remaining methods can have simpler implementations with distinct keys than if duplicate search keys are allowed. For example, the methods remove and get value will either find the one value associated with a given search key or discover that no search key exists. If we permit duplicate search keys, the method add will add every given key value entry to a dictionary. The methods remove and get value must deal with multiple entries that have the same search key. For example, which entry should be removed or returned? The method remove could either remove the first value it finds or remove all the values associated with this given search key. If get value returns an object, it could return the first value it finds, or you could modify get value to return a list of values as an example. For simplicity, our examples will assume distinct search keys. So now let's look at the specifications for our ADT dictionary with distinct search keys. Like the interfaces for the ADT's list and sorted list, this interface specifies the data type of its entries generally. Since the search keys can have a data type that differ from the type of the associated values, we will use two formal type parameters, K and V.
So I've already mentioned this, but this is what the .java interface that you're going to be implementing. It's going to have that angle brackets K comma V closed angle brackets for that. So two, not one generics.
K represents the data type of the search keys, and V is the type of the associated values. The operations for our ADT dictionary are add a new entry to the dictionary, given a search key and associated value. Since we're requiring distinct search keys, we need to specify a behavior for when the given search key duplicates a key already in our dictionary. In our dictionaries, we'll always replace the corresponding value with a new value sent as a parameter and return the previous value that corresponded to the search key. Remove an entry given its associated search key. Since the client needed to use the search key to specify the entry to remove, we only need to return the value part of the pair or null if the search key was not found. Get value retrieves the value associated with a given search key, and this returns the value associated with the search key or null if the search key does not exist. Contains a similar but only returns a Boolean to indicate whether or not the dictionary contains a given search key. We have two methods to return iterators. One iterator traverses all the search keys in the dictionary, and the second traverses all the values in the dictionary. Each iterator provides sequential access to the search keys or values respectively.
So this is how we can get either let me try and pull up this graphic that I showed. So this graphic here, so you have the value iterator that's on one side, the key iterator that's on the other. And so those are things that we can sequentially get that information, one or both of them at the same time.
The iterator for traversing all values permits the client to traverse the entries in the dictionary without knowledge of the search keys. Lastly, we have the isEmpty, getSize, and clear methods, and each of these methods operate as you'd expect them to. IsEmpty detects whether a dictionary is empty, getSize gets the number of entries in the dictionary, and clear removes all the entries from the dictionary. When we look at our implementation in a future lecture, we'll need to decide on a manner to store a collection of pairs of objects K and V, where K is the search key and V is the corresponding value, and also store the number of key value pairs in the collection.
Okay, so that's the basic introduction of a dictionary. And literally, we just got to a point where we were explaining what the different methods do. And so this has some more capability and for us to unpack. And hopefully over the next handful of lectures, it'll start to be clear if this is your first time that you have an experience with this. Okay, we'll get a chance now just thinking a little bit about samples of a dictionary. And so we'll just go ahead and do this next video node, and then we'll click over to Eclipse and look over that for a few minutes.
Okay. This lecture demonstrates how to use the ADT dictionary to represent a telephone directory. The most frequent operation performed on a telephone directory is the retrieval of a telephone number given a person's name.
So here we're looking at a telephone directory, and it's saying what is the most typical thing that you have. And so another thing to think about, how often are people going to add elements or delete elements from this dictionary? Or if they even have that at all, that actually could be impacting how you're going to be focusing on your implementation.
Thus, using the ADT dictionary to represent a telephone directory is a good choice. Clearly, the name should be the search key, and the telephone number should be the corresponding value. Often, but not always, retrieval is more efficient when the dictionary is sorted. Additionally, a sorted dictionary would make it easier to create a printed directory with entries alphabetized by name. To simplify this example, we'll assume the directory will contain distinct names with no duplicates. A sorted dictionary will represent the data, which consists of name-number pairs. So our class telephone directory contains an instance phone book of a dictionary. At this point, we won't concern ourselves with the implementation details of the dictionary, other than needing to know that each person's name can be an instance of the name class that was first encountered in the appendix that reviewed classes. And the telephone number can be a string stored without embedded blanks. A major task, at least initially, is to create the directory from the available names and telephone numbers. So we need a method to add a person to the directory.
So we can see that now we've started to get into the syntax, like they said that the telephone numbers don't have any dashes or spaces. Here are the kind of things that we can do in terms of querying for the name. And so those are some things that are going to be helpful for us as we get into the next level of details.
We may also want to print out the entire telephone directory so we can distribute it to other people. Having this data in a text file will make it convenient to reload in the future, and we'll need to have a method to write the directory to a file and read it into the program later. These two methods will not be covered in this lecture. Before we implement the class telephone directory, let's consider its use. A client would create an instance of telephone directory. Names and telephone numbers would then be added to the directory using the add person method. Here, we create 3 names and the associated telephone numbers and add them to our telephone directory. To find a person's phone number, we will ask the user for the person's first and last name, and then search the directory for that person's telephone number.
So the implementation is going to have this method, this add person. And so this is, in this case, we're not reading a file. We're actually doing it, hard coding it one at a time.
Once the user's entered the first and last name, we need to use those to create a name object that can serve as a search key when looking for a phone number. To save some space, this code snippet assumes there'll be no errors in the user input. When you implement this code yourself, be sure to check that the user's entered valid data. Once we've created a name object, we can call the directories.
In what I showed you in the lecture note, it showed the checks for valid data. If you may want to review that in the lecture notes.
get phone number method to retrieve the person's phone number for us. There's a chance our phone directory does not have an entry for the person, so get phone number won't find the phone number. In that case, we need to display a message that the person is not in the directory. Otherwise, we'll find the phone number for the person and we can display it for the user. In our telephone directory class, we'll use a dictionary to store our collection of names and telephone numbers. The key will be of type name and represent the person, and the value will be of type string and represent the person's phone number. The constructor instantiates a sorted dictionary for us to use. And then retrieving a phone number with the get phone number method is straightforward, since we simply need to return the value that matches the search key or the person's name that was given to us. When we go to add a new entry to our phone book, there's a chance that the person already exists. Since our dictionary implementations do not permit duplicate search keys, the dictionary's add method will replace the telephone number of that person with the new value. In this situation, the dictionary's add method will return the old phone number instead of null. We need to test for this and inform the user that the person's phone number was updated instead of added. To print the phone book, we're again going to use the iterators provided by the dictionary. We first instantiate a name iterator to go through the search keys, and then a string iterator to traverse the corresponding values. Then, while there's still another search key in the phone book, we display the next key and the next value. Using iterators greatly simplifies this process, but notice that we need one iterator for the search keys and one for the values, and that both must be incremented together so that the value retrieved always matches the current search key iterator. An alternative implementation uses only one iterator, the search key iterator, and retrieves the corresponding phone number value using the dictionary's get value method. While this may be safer in that it ensures the value always matches the search key, it can be much slower, especially for linked implementations in a dictionary.
Okay, so that's a good breaking point for us to, as we're trying to get an introduction to looking at dictionaries, but let's go ahead and spend a little bit of time. I'll go over the two searching types, and we had an array sort that we talked our last lecture, and then we talked about a chain or link sort today, and this will be a little bit of review, and then I'll see if anyone wants to share some of their code in just a minute or two. So these aren't like a full implementation. It's just trying to show how we would go about doing these functions. And so first of all, we do an implementation of an array search. And so here we just call it array searcher. That's a class. And so this is from our chapter that we just covered before getting into dictionaries. And so this is just setting things up. So we have the class array searcher. So here we have an unsorted array for an entry iteratively. And so this is one of the methods that we're looking at here. Unsorted. This is unsorted array recursively. And so we have an iterative approach. We have a recursive approach for an unsorted array. And so then we have a private methods search that is called for within this public method. And so this is just the coding practice that we have been introduced to with some of the things that they're doing in the textbook approach here. And so we have to go one item at a time. And so, but this is a recursive method. So rather than an iterative method, that the way that we see here in this first one. Then we have a sorted array, and we have first the recursive approach. And let's see, did I miss one? So we have unsorted, unsorted. Then we have sorted. This is a recursive approach. So we have those three different things. And then we have this display, which is gives us a chance to see all of that working. The driver for both of these cases are identical, except that one is calling the array searcher. So for an unsorted array, an unsorted array, a sorted array, for those three things that we have. And then we print out the results. And if I just go over to the linked, it just it says unsorted chain, unsorted chain, sorted chain. So it has those. Here we have the array searcher. And for sorry, here is the in unsorted array iterator, in unsorted array iterator, in sorted array recursive. And so those are the three things that we have here that are laid out for this one. And so this just gives us, shows us what the output would look like for each of those three cases. I know I got two drivers open, so I'm not sure what will happen if I go here, which one will pull up. Okay, so that does the one that I just had here. So this matches what's laid out there. Then for the implementation of the chain searcher, so we need to have this general construct again. The things need to be comparable for us to make things work. We have to have a private class node. And so we initialize the first node, the last node, and the number of entries. The number of entries helps us with our big O notation. And so we have the unsorted chain iterative. We saw that in the video note. We had the unsorted chain recursive. We have that. Then we have the sorted chain iterative. And we don't have the sorted array recursive. We saw that that was not something that was worthwhile doing. We have a big O notation of n squared. And so this ends up matching the same three fields, the same three options that we had for the array search. We have a couple of other things. We have clear, get length is empty. Couple other methods here, add to end and display. So all of these things are laid out here. We have a few private things here. We have a private method, initialize the data fields, and then we have the private class node that we need when we do a linked implementation. And so if we do a driver for that, just run it and it should look pretty much the same as the other one, but except we're using things with a linked implementation for that. Any comments or questions on that? You guys tracking? Did that make sense? Okay, good. Well, I also wanted to leave a little bit of time if anyone would like to share some of their code. We are now getting to a point where you've done a variety of ADTs and maybe you'd like to just do some class participation. And so anybody feel like sharing what they have? The last one we did was a list. And if not today, maybe we can do it when we come back after our spring break. Grace, you want to just give us a heads up? You want to do it now or you want to do it in a couple of weeks, share some of your code?
Probably in a couple weeks.
Okay. And it sounds like David is saying the same thing. Okay, well, we'll plan on doing that. I think we'll have some more time. yeah, I think we're doing a good job of getting through the course material. So anyway, I hope you have a wonderful time off, and please do reach out as you have been so far if you do have any comments or questions, and I'll be glad to engage with you. Okay? Take care. God bless now.
Thank you.
Thank you, you too.